Assalamu alaikum. Welcome, students. In the last lecture, we started the topic of rotational mechanical systems, in which we discussed the torque angular velocity and torque angular displacement relationships of all three basic elements present in the system. We then created analogies between rotational mechanical system and the electrical quantities. And then towards the end of the lecture, we did a simple problem in which we uh, learn how to create a electrical equivalent network and how to write equation of motion at a specified node. Now let's start today's lecture by doing a problem with three independent motion in the system. So question is, write but do not solve so, the Laplace transform of, of the equation of motion uh, for the system below. So system is D J1 B1, spring J2, damper J3, and again damper. This is spring K, this is B2, this is B3, this is B1. This is motion theta 1, this is motion theta 2, and this is motion theta 3. And here we have applied the torque at theta 1 node. So we have to write equation of motion at theta 1, theta 2, and theta 3. So first draw the equivalent network. Drawing equivalent network. So torque applied at theta 1, which is uh, T of T, and here is J1, J1, and B1 between theta 1 node and reference B1, and spring is connected. This spring is connected in between theta 1 and theta 2. Here is the spring, and now we arrive at the node theta 2. At this node, J2 is present between node and reference node. And then we have this B2, which is connected in between theta 2 and theta 3. So this is theta 3 node, and at theta 3 we have J3, and at theta 3 we also have a damper connected in between this damper connected between theta 3 and reference. This is B3, and this is B2. Uh, this is theta 1 node, right from here to here, this is theta 2 node, and this represents theta 3 node. uh, I hope you can and this is a reference node. I hope you can write the equation of motion at all these nodes. So I am skipping this problem. uh, so let's do another problem. Question is, find the transfer function uh, g of s is equals to theta 2 of s by t of s uh, for the rotational mechanical system shown below. So here is the system. This is J. Uh, Here is the spring, mm, damper, spring K1. This is B1, and here we have damper, and here we have another spring connected at reference. This is K2 and this is B2. Here the independent motion is marked theta 2, and motion here is theta 1, and torque is applied here. Sorry. So values of these elements are J is equals to 1 kg meter square, K1 is equals to 1 Newton meter per radian, and similarly also it is equals to K2, and B1 is equals to B2 is equals to 1 Newton meter second per radian. So these are the given values of these elements. Now we have to find the transfer function that relates this motion with this torque. So first, drawing the equivalent network. Drawing equivalent network. So applied torque, which is at theta 1, and here we have J connected between node and reference node, and the spring and the damper K1 and B1 are these K1. This K1 and B1 is connected in between theta 1. This is theta 1 and this is theta 2 node. So at this point we have another spring and another damper which is connected in between theta 2 and the reference. So I'm drawing it this way. This is K2, this is B2, this is B1, and this is K1. This is node theta 1 and this is node theta 2. Now you can write the equation of motion at theta 1 and theta 2. We have learned it, so you can solve the problem from here. So I am leaving it. Now let's move our discussion further. Rotational mechanical systems with gears. Rotational systems can have gears. You guys know it better than me. Gears are the devices which provide mechanical advantage to the rotational system. Conventional automobile are the best example of rotational systems with gears. Now we can write this equation for the two gears meshed together. Theta 1 over sorry theta 2 over theta 1 is equals to R1 uh, over R2 is equals to N1 over N2, where this theta 2 and theta 1 are the angular displacements of gear 1 and 2 respectively. R1 R2 represents radius of gear 1 and 2 respectively, and N1 and N2 represents number of teeth in gear 1 and 2 respectively. Now there is one condition for this relation to be true, and it is the distance between two consecutive teeth are the same for both meshed gears, which is also known as pitch of the gear. Now if we assume a lossless gear system in which gears do not absorb or store energy, that is, energy in at gear 1 is equal to energy out at gear 2. Then we can write this relation for two meshed gears. T1 theta 1 is equals to T2 theta 2. Energy input at gear 1 is equals to energy out at gear 2. Now combining these two equations, we will get T2 over T1 is equals to theta 1 over theta 2 is equals to N2 over N1. From this equation, we can comment that torque is directly proportional to the number of teeth present in the gear, and angular displacement is inversely related to the number of teeth present in the specific gear. Now, this is the equation we will use frequently to solve the rotational mechanical systems with gears. Now, let's solve a problem related to the geared mechanical system. Question is, find the transfer function theta 1 of s by t of s for the system below. So system is here we have J1, J sorry J1, B1, J2, and B2 and K2. This is the symbol of gear, two meshed gears. Number of teeth in this part of the gear is N1, and number of teeth at this part of the gear is N2. And here the applied torque is T1 of t, and motion here is theta 1, and motion here is theta 2. Now you can see I have marked here the rotation as clockwise and here anti-clockwise. Since it is in gear, the rotation at first gear is opposite of motion in the second gear. So if the rotation of motion in gear 1 is clockwise, then at gear 2 the motion will be anti-clockwise. So we have to find the transfer function that relate theta 1 with t1 for this whole system. So first draw the equivalent network, drawing equivalent network for this mechanical system. So here torque T1 applied on J1, uh, B1, and the input gear, which is marked as gear 1, and this is coupled with second gear, which is actually source for this whole system. So and this gear is taking energy from this gear. So we arrive here at theta 2 node, and at theta 2 we have J2, and K2 and B2 are from node to reference node. So K2 and B2. So here is the equivalent network for the above system, theta 1 and theta 2. Number of teeth present in this gear is N1 and at this gear is N2. Let's say assume we have the torque absorbed in this gear B TA, and let's say torque supplied by this gear to this whole system B TB. Now we can relate TA and TB using this relationship. So let's solve the problem, writing equation of motion at theta 1. So writing equation of motion at theta 1. So T1 is equals to J1 d square theta 1 by dt square plus B1 d theta 1 by dt plus TA. This will become equation number 1. So torque applied at this node is absorbed in this B1, this J1, and in this gear. This gear is also absorbing energy. So in this equation we have written the torque supplied is equals to torque due to this, and this term. Now writing equation of motion at theta 2, writing equation of motion at theta 2. So TB is equals to J2 d square theta 2 over dt square plus B2 d theta 2 over dt plus K2 theta 2. That will become our equation number 2. Now we can use this relationship to convert this TB into TA and this theta 2 into theta 1, and we will put the resulting equation in this equation to convert to arrive at the equation having only t1 and theta 1, which will then be used to find the desired transfer function theta 1 over t1. This is t1. So let's follow the procedure. Uh, we know that uh, Ta over Tb is equals to N1 over N2. Uh, Torque at this gear divided by torque at this gear is equals to number of teeth in this gear divided by number of teeth in this gear. So, or I can write Tb as N2 over N1 Ta. That will become equation number 3. And we also know that uh, theta 1 over theta 2 is equals to N2 over N1. Uh, Angular displacement at this gear divided by angular displacement at second gear is equals to number of teeth in second gear divided by number of teeth in first gear, since the relationship is inverse for the angular displacement. So theta 2 will be equals to n1 over n2 theta 1. That will become equation number 4. Now put equation 3 and 4 into, put 3 and 4 into, we get in this equation number 2. So this Tb will become N2 over N1 Ta is equals to J2 N1 over N2 d square theta 1 by dt square. If we put theta 2 equals to N1 over N2 theta 1, then derivative of the coefficient will comes outside of the derivative. So here we go. Uh, Similarly, sorry, b2 or n1 over n2 d theta 1 by dt plus k2 n1 by n2 theta 1, or moving this n2 by n1 to this side of equation. So Ta will be equals to, and then this n1 this will become n1 by n2, and we multiply it with this n1 by n2, so it will become n1 by n2 whole square. So Ta equals to I'm writing below Ta equals to n1 over n2 square j2 d square theta 1 by dt square plus n1 by n2 whole square b2 d theta 1 by dt plus n1 by n2 whole square k2 theta 1. Now this will become equation number 5. Equation number 5. Now we will put this equation number 5 in 1. So putting it, put 5 in 1. So T1 will be equal to J1 d square theta 1 by dt plus B1 d theta 1 by dt plus N1 by N2 whole square d J2 uh, d square theta 1 by dt square uh, plus n1 over n2 whole square b2 d theta 1 by dt plus n1 by n2 whole square k2 theta 1. So now you can solve this equation by taking Laplace transform on both sides of the equation, and then separating this theta 1 to find the desired transfer function theta 1 by t1. So I am leaving this problem for you to solve it. Uh, Now let's move towards the last topic of the chapter, electromechanical system transfer function. As the name suggests, electromechanical systems are hybrid of electrical and mechanical systems. Uh, in our course, DC motor is included as an electromechanical system. Since input to the motor is an electrical quantity, that is voltage, and output of the motor is angular velocity, which is a mechanical quantity. So we will derive transfer function of armature controlled DC motor specifically. The schematic of DC motor is, I'm drawing it. The schematic is resistor, inductor, applied voltage EO of T, RA, LA, VB of T, TM, and so this is the schematic of a DC motor. Here, field is generated by either a permanent magnet or by an electromagnet. Uh, the rotating part of the motor is known as, this is the rotating part. This rotating part is known as armature. Armature is not always rotating. A quick search on Wikipedia uh, reveal that armature is a component of an electric machine which carries alternating current. Uh, this armature can be either on the rotor or the stator, depending on the type of the electric machine. So we can say armature is that part of the motor which carries AC current. Okay, even in case of DC motor. So the current here IA is flowing in this armature. We are considering in this case the armature is the rotating part, and the fixed field is on the stator. So the current IA is flowing in the armature. Due to this current, the rotor of the machine will experience a force which will be F is equals to BLIA. L is the length of a conductor, which is represented by R and L. Length of the conductor in the armature. B is the magnetic field strength produced by this fixed field, and Ia is the current that is flowing from the armature circuit. So due to this force, rotor starts moving. This part starts moving. Now there is another phenomena that occurs in the motor, which is when a conductor moves at right angles to a magnetic field, it generates a voltage at the terminals of the conductor. Uh, since the current carrying armature is rotating in a magnetic field, the generated voltage it will generate a voltage which we call the back EMF, represented here by VB. This back EMF VB is proportional to the speed, so we can write this VB of t to be equals to KB d theta m of t by dt. So this is the omega m, which is the angular velocity of the machine. So this back EMF is directly proportional to this quantity. So removing the direct proportionality sign of the direct proportionality, we get this constant KB, which is called the back EMF constant. Now mark this equation to be 1. Now if we take Laplace transform on this equation, we will get VB of S is equals to KB S theta m bracket S. Mark this equation to be 2. This bracket S represents function of S. This VB is function of S and theta m is function of S. Now applying KVL in this circuit, the applied voltage EA is equals to the voltage drop across this and the voltage due to this. So applying KVL, we will get RA IA of S plus LA S. I am directly writing this KVL equation in Laplace transform. LAS IA of S plus VB of S is equals to this voltage. This voltage is equals to voltage drop across this and this VB. So equals to the applied voltage in S domain. So mark this equation to be 3. So now the torque in the motor, the torque in this rotating part is proportional to the armature current flowing in this circuit. So I can write directly in torque equation in S domain as Tm of S is equals to Kt Ia of S. Again, this Kt is the constant known as the torque constant, which is inserted when we remove the direct proportionality sign, and I have written directly this equation in S domain. Mark this equation to be equation number 4. Now from equation 4 I can calculate the value of Ia. So from 4, Ia of S is equals to Tm of S over Kt. This is equation number 5. Now put this equation number 5 in equation number 3. So 5 in 3, we will get RA plus LAS bracket Tm. I am omitting the sign of this of S sign, since it is creating confusion. Tm and Kt plus Kb S theta m is equals to Ea. Now this is equation number 6. Now torque, this torque developed in the motor is used to drive a load connected to the shaft of the motor. Typically loading on motor can be modeled as like this: inertia, damper, Bm, Jm, and Tm of t and theta m of t. So The load on the motor can be modeled typically like this. Load can be modeled by Jm and Bm. This Jm is equivalent inertia including both the armature inertia and load inertia. Similarly, Bm is equivalent friction or damping, including damping due to armature as well as due to load. So from figure I can write the equation of Tm as I am directly writing it in S domain. Tm is equals to Js square plus Bms, this is m, and theta m. Mark this equation to be 7. Now put equation number 7 in equation number 6. So 7 in 6 we get RA LAS sorry RA plus LAS JM S square plus BM S whole over KT plus KB S theta M. Here is theta also is equals to EA. Now mark this equation to be equation 8. So I have put this equation, put the value of Tm from this equation to this one. So we get this equation number 8. Now in practically the value of inductance in the motor is very small compared to this Ra. So we can neglect this value. So put La is equals to 0. So this equation 8 will become I am writing it directly RT sorry RA over KT JMS plus BM plus KB S theta M is equals to EA. I have taken S common from S and theta M common from this factor and this factor also. So we get this equation. So theta M over EA, which is the transfer function, can be written as the simplified version is KT RA JM over S into S plus 1 over JM BM plus KT KB over RA bracket. Now this is the transfer function of the motor. Mark this equation to be 9. So now you can see here the output is the mechanical quantity, which is the angular displacement, and input is the electrical quantity, which is the applied voltage. Now we can also write this equation in omega m, which is the angular velocity. If I move this s here to this side of equation, so this will become s theta m, and s theta m is equals to omega m. So I am writing equation 9 as directly omega m over EA is equals to KT over RA JM S plus 1 over JM bracket BM plus KT KB RA. So again, this is the transfer function in which output is the angular velocity. Mark this equation to be 10. Uh, Now here you can see we have KT and KB. These are the machine constants. We can evaluate the machine constants using the dynamometer test, uh, where dynamometer measures the torque and speed of the motor. Let's see how we can evaluate these constants using dynamometer test. So to find it, put put LA is equals to 0 in equation number. Let me check in this equation. Put LA is equals to 0 in equation number 6. Put LA is equals to 0 in 6. We get RA Tm of S over Kt plus Kb S theta m of S is equals to Ea of S. Now taking inverse Laplace transform on both sides of this equation, I will get the quantities in time domain. So Ra over Kt, this will become Tm in time domain, uh, plus Kb. This S theta m will become d theta m by dt, which I can write omega m. So Kb omega m of t is equals to this voltage will become the will convert into time domain, so Ea of t. Now rearranging this equation, I will get Tm is equals to, I am omitting this of t sign, Tm is equals to minus Kt Kb over Ra omega m plus Kt over Ra Ea. So this is the torque speed equation of the DC motor. This is torque speed equation. Now here you can see, if I am applying the constant voltage, then this part will become constant. So here this omega m will be at x-axis and this will be at y-axis. So I am plotting this. If you observe this equation, I can write generally this equation as y is equals to mx plus b, where this part represents slope and this whole part represents including Ea to be the y-intercept, which is b. So the plot of this equation will be like this, uh, omega and omega m, and this is Tm. Here you can see when motor starts, it will be at maximum speed. So here we have the maximum speed at approximately zero load. So as we start loading the motor, the speed of the motor starts decreasing and torque starts increasing, and there will a time come when motor will eventually stop. So this point, at this point motor will stop, and I can mark this torque to be T stall. This is the maximum amount of torque which a motor, DC motor, can supply, and I can mark this point to be omega no load. This is the maximum speed a motor can develop at its shaft. So this point is omega no load, and this point is T stall. Here torque is 0 and here omega is 0. I can also shift this plot like this by changing this voltage Ea. So I can mark this to be uh, Ea1 and Ea2. The more I will apply the voltage, the more it starts shifting towards right way, and the less voltage I apply, then it starts moving downward like this. This EA2 is less than EA1. So putting these points, T stall points and omega no load point in this equation here, the coordinates are 0, comma, x-axis is 0 and T stall, and here coordinates are omega no load, comma, 0. So putting these points in this equation, mark this equation to be uh, 11. So uh, so we will get KT. I'm directly writing it. You can solve to find this relation. T stall first, T stall EA, and second, by putting this point I will get KB is equals to EA omega no load. So you can put this coordinate to arrive at this equation, and you can put this coordinate in equation number 11 to arrive this equation. So these are equation 12 and 13. This T stall and omega no load can be found using the dynamometer test. So here you can see how we can use dynamometer to find the machine constants KT over RA and KB. Now if you put KT over RA directly in this equation and KB in this equation, I can find these constants, and mostly the loading on the machine is given, so Jm and Bm are given. So by using dynamometer test plus loading on the motor, I can find the transfer function of the DC motor. So that was the end of the topic, and it was the last topic of this chapter. Now we will start chapter 3 in the next lecture. Thank you. Allah Hafiz.